At this point, we have a couple good interpretations for what a derivative is telling us, or a couple situations where we know the derivative tells us something interesting. One is sort of the situation that inspired us to come up with the derivative, and that is if we have a graph then that's given by y equals f of x, then the derivative of the function at a point actually tells you the slope of the tangent line at that point. So that's sort of an interesting geometric situation where the derivative comes up. Also, we've seen that if you have a function that describes the position of an object as it moves back and forth along a line, kind of in a one-dimensional situation, then the derivative of that function tells you the velocity as a function of time, and the second derivative tells you the acceleration. But I mean, if the derivative is really as important as I've been claiming this whole time, then surely there must be some other situations where the derivative comes up, or where the derivative sort of tells us something interesting. And in fact, almost any situation where you have a function, the derivative of that function is going to tell you something interesting. But it's not always clear what that thing is. So let's look at a couple examples. So suppose we're manufacturing, so maybe we're selling hand soap, and suppose that the cost of producing and selling X tons of hand soap is C of X, so I chose C for cost. Then what would the derivative measure in this case? I mean, if we had a formula for C of X, we could calculate this derivative, but there's no reason to calculate it if you don't know what the derivative is actually describing, what sort of thing it's measuring. So to understand what it's measuring, let's interpret dc dx. Now, if we have a function, if c is a function like this, then dc dx, geometrically speaking, it's the slope of a tangent line, but that's how we came up with the derivative is we actually used a nearby secant line to approximate the tangent line. So in general, this derivative is going to be approximately the change in x that produced this secant line divided by the change in the cost that produced this secant line. So it's approximately the change in cost over the change in x. Not exactly. You can see the tangent line and the height of the function aren't exactly the same when you move over delta x, but they're pretty close. So what would this sort of ratio tell you? So here we're changing production by an amount delta x, and that causes a change in cost, delta c. So when you divide those two, what you get is approximately the increase in cost per unit increase in the production level, the production level x. In other words, it's telling you if you increase your production level by 1, then the cost will increase by approximately this amount. That kind of makes sense because in this situation, the units for this derivative would be dollars per ton. So it kind of makes sense that what this quantity is telling you is the price increase or the cost increase per ton. This is actually a quantity that's interesting in many business situations. This is called marginal cost. So marginal cost is the increase in your costs if you increase production by 1 unit. In fact, there's a whole collection of related quantities in sort of business analysis situations. Marginal cost is the cost increase by increasing production 1 unit. There's, of course, marginal revenue. If you increase your production 1 unit, how much your revenue would increase, and marginal profit as well. If you increase your production by 1 unit, how much your profit would change. And all of these are just derivatives. So marginal cost was the derivative of cost with respect to x. Marginal revenue is just the derivative of revenue with respect to x. And marginal profit is the derivative of profit with respect to x, where x is your production level. So for example, we can use this idea. Suppose that the cost of producing X tons of hand soap is given by this formula. Let's find the production level that makes the marginal cost as small as possible. In many business situations, analyzing the marginal cost or marginal profit is a good thing to do because you're already at some production level and you want to figure out what would happen if I increased production a little bit or decreased it a little bit. So often marginal cost is something you want to know about. Well, to find marginal cost, marginal cost, that's just the derivative of C with respect to X, or derivative of cost with respect to production level. So we can use the power rule to calculate that. That's 3 over 160 times x cubed minus, looks like it's 3 over 20 times x plus 10. And we want to know, so the question was, when is this as small as possible? Well, in general, we don't really know how to answer that question, but for this, oops, I made a mistake here. This cubed should be squared. In general, we don't know how to find the minimum, the smallest output that a function produces, but for this kind of function, we do, right? This is a quadratic, and it's opening upwards because the squared term has a positive coefficient, and so the minimum is at the vertex. And you might remember that the vertex of a parabola is at x value minus b over 2a. So that's going to give us minus 3 over 20, sorry, plus 3 over 20, because there's a minus coming from b itself, and then there's a minus sign in the formula. So plus 3 over 20 over 2 times 3 over 160. All right, we should simplify this fraction. So the 2 makes this an 80 down here. And rather than dividing by a fraction, let's multiply by its reciprocal. So 3 over 20 times 80 over 3. So these 3's cancel, right? We can simplify this. That leaves us with 4. So 4 tons. So the production level that produces the smallest marginal cost is 4 tons. If we wanted to know the actual marginal cost at this production level, we would just plug it into this marginal cost function. Another interesting situation where the derivative tells you something a little bit surprising is this one. So suppose we have a metal rod and x, so here's our metal rod, and x measures the distance from the left-hand end of the rod. So we're sort of labeling positions along the rod using this variable x. So over here is x equals 0, and then over here is x equals the total length of the rod. So we can make a function called the cumulative mass function that is a function of x, and it just tells you how much mass is between the left-hand end and the position x. So the mass between the left-hand end and position x is m of x. So in this case, what would dm dx measure? Well, again, dm dx, the derivative of m with respect to x, it's approximately a change in mass, or the change in mass you get by changing x a little bit. But what would that look like in this case? So if we're at this x value and we moved over a little bit by delta x to this x value, that produces, right, we're adding this much mass to the situation. And if you have sort of a new chunk of mass, and you divide by the length that it came from, what that actually gives you is a density. This kind of density where we're in a one-dimensional situation rather than a three-dimensional situation because we're dividing by a one-dimensional thing instead of a three-dimensional volume. This kind of density is called a linear density. So delta m over delta x, this is the average linear density. So what does the derivative tell you? Well, it tells you sort of the instantaneous version of whatever the this ratio tells you. So dm dx, I guess we could call this the point density, the point linear density at position x. And often we'll omit this adjective point density and just say the linear density at position x. This is kind of a surprising thing because it's this construction of a cumulative mass function. It's a little bit on the artificial side, so you might think that the derivative of this function would be just as artificial and sort of uncommon or meaningless. But actually, the density of an object is something that's of great interest if you're happen to be doing, I don't know, some sort of engineering or physics kind of situation using these metal rods. For example, suppose that we have a 50 centimeter rod, and its cumulative mass function is given by this, square root of x plus 2, where x is measured from the left hand. So let's find the density function for this rod. And this is a linear density again. So the density function is just dm dx. So we'll just take the derivative of this. Of course, the derivative of the constant term is 0. So let's take the derivative of the square root term. That's 1 over 2 square root x. And that's just using the power rule, right? If you use the power rule on x to the 1/2, you get 1/2 x to the minus 1/2, which is that. Okay, so what's the density of the rod at its middle? Well, the middle of this rod, since this rod is 50 centimeters long, the middle of this rod is at 25 centimeters. So we're going to get 1 over 2 square root 25. So that's 1 over 10. What are the units for this? Well, as for any derivative, the unit is going to be the derivative of the thing in the top. I hesitate to call it a numerator because this isn't really a fraction, remember, but the units are going to be the unit for the thing in the top, which is grams, I think. I didn't say, but let's say this is in grams. And divided by the unit for the variable on bottom, which that's x, that's in centimeters. So 1/10 of a gram per centimeter. So this is a very undense rod. Maybe it's made out of styrofoam or something. All right, so what is the density of the rod at its left end? That's going to be the derivative, dm dx at 0. Well, if we try to plug in 0 to this function, that doesn't really make any sense because we end up dividing by 0. What we could do instead is take the limit as x goes to 0 of dm dx. So this is the limit. Oh, and we can't have negative x values, so we'd better take the limit from the right. So this is the limit as x goes to 0 from the right of 1 over 2 square root x. Now as x goes to 0 from the right, this part in the denominator here is a very small number because we're close to 0, but it's also positive. So it's a positive small number. So we're getting sort of, in the denominator, we're getting a small positive. And 1 divided by a small positive, that's a big positive. So the limit is positive infinity here. This is a little bit surprising because this rod has finite mass. I mean, if we evaluated our mass function at 50, we get a finite number. Square root of 50 is, what, 5 root 2, I think, plus 2. So this is in grams. This is the total mass of the rod, but at the very, very left-hand end of the rod, the density is actually infinite. So that's a little bit surprising, but it does work out. The reason that this works out is because it's true that the left-hand end of the rod is very, very dense, but it also is very, very small, right? The this infinitely dense portion of the rod is just this very left-hand face, but of course the left-hand face is infinitely thin, so there really isn't much length there to accumulate mass, as the density is infinite.